So I had to leave you in the middle of something pretty exciting. So I'll come back and take it from there. So how does that come into play? For that, I want you to take the simple example where the temperature enters. That is in the relation PV equal to some constant times temperature. What do we think should be on the right-hand side? What is going to control this particular constant for your given experiment? Do you know what it might be proportional to? Amount of gas. That's true, because if the amount of gas is 0, we think there's no pressure. When you say amount of gas, it's a very safe sentence, because amount measured by what means, by what metric?
Probably number of particles.
Right. Suppose you were not aware of particles. Then what would you mean by amount of gas?
Mass.
The mass. Now, if you guys ever said moles, I was going to shoot you down. You're not supposed to know those things. We are trying to deduce that. So put yourself back in whatever Stone Ages we were in. We don't know anything else. Mass would be a reasonable argument, right? What's the argument? We know that if you had some amount of gas producing a pressure and you put twice as much stuff, you think it'll produce twice as much pressure. Same reason why you think the expansion of a rod is proportional to change in temperature times the starting length. So this mass is what's doing it, so it's proportional to mass. It's a very reasonable guess. So if you put more gas into your piston, you think it'll produce more pressure. That's actually correct. So let's go to that one particular sample in your laboratory that you did. So put the mass that you had there. Then you should put a constant still. I don't know what you want me to call this constant. Say C prime. This constant contained everything, but I pulled out the mass, and the remaining constant I want to call C prime. But here is what people found. If you do it that way, the constant C prime depends on the gas you are considering. If you consider hydrogen gas, let's call that C prime for hydrogen. Somebody else puts in helium gas. Then you find that C prime for helium is 1/4 C prime for hydrogen. If you do carbon, it's another number. C prime for carbon is C prime for hydrogen divided by 12. So each gas has a different constant. So we conclude that, yes, it's the mass that decides it, but the mass has to be divided by different numbers for different gases to find the real effect it has in terms of pressure. In other words, 1 gram of hydrogen and 1 gram of helium do not have the same pressure. In fact, 1 gram of helium has to be divided by 4 to find its effect on pressure. So you have to think about why is it that the mass directly is not involved. Mass has to be divided by a number, and the number is a nice round number. 4 for this and 12 for that. And of course, people figured out, this is a long story I cannot go into, but I think you all know the answer. But now you're allowed to fast forward to the correct answer, because I really don't have the time to see how they worked it out. But from these integers and the way gases reacted and formed complicated molecules, they figured out what's really going on is that you're dividing by a number that's proportional to the mass of the underlying fundamental entity, which would be an atom, in some cases molecule, but I'm just going to call everything as atom. So if things like carbon as atoms weigh 12 times as much as things called hydrogen, then if you took some amount of carbon, you divide it by a number like 12 to count the number of carbon atoms. In the case of hydrogen, you want to count the number of hydrogen atoms. So that what really you want here is not the mass, but the number of atoms of a given kind. We are certainly free to write either a mass or the number of atoms, because the two are proportional. But the beauty of writing it this way, if you write it in this fashion, where this is a new constant k, k is independent of the gas. So you want to write it in a manner in which it doesn't depend on the gas. You can write it in terms of mass. If you did, for each mass you got to divide by a certain number. Then once you divide it by the number, you can put a single constant in front. Or if you want a universal constant, what you should really be counting is the number of atoms or molecules. So you couldn't have written it that way till you knew about atoms and molecules. And people were led to atoms and molecules by looking at the way gases interact. And it's a beautiful piece of chemistry to figure out really that there are entities which come in discrete units. Not at all obvious in the old days that mass comes in discrete units called atoms, but that's what they deduced. So this is called the Boltzmann constant. The Boltzmann constant has a value 1.4 times 10 to the minus 23, let's see, joules, Kelvin, that's it. Or joules Kelvin or degree centigrade. So now what people like to do is they don't like to write the number. Because if you write the number in a typical situation, what's the number going to be on it? Take some random gas, 1 gram, 2 grams, 1 kilogram, doesn't matter. The number you will put in there is some number like 10 to the 23 or 10 to the 25. That's a huge number. So whenever a huge number is involved, what you try to do is to measure the huge number as a simple multiple of another huge number, which will be our units for measuring large numbers. For example, when you want to buy eggs, you measure in dozens. When you want to buy paper, you may want to measure it in thousands or 500s or whatever units they sell them in. It's a natural unit. When you want to find intergalactic distances, you may use a light year. Likewise, when you want to simply count numbers, it turns out there's a very natural number called Avogadro's number. Avogadro's number is 6 times 10 to the 23. It has no units, it's simply a number, and that's called a mole. So you can ask yourself, what's so great about this number? Why would someone think of this particular number? Why not some other number? Why not 10 to the 24? Do you know what's special about this number? A mole is such that 1 mole of hydrogen weighs 1 gram. And hydrogen is the simplest element. The nucleus is just a proton, and the electron mass is negligible. So this, if you like, is the reciprocal of the mass of hydrogen. In other words, 1 over Avogadro's number is the mass of hydrogen in grams of a hydrogen atom in grams. So if you decide to measure the number of atoms you have in a given problem in terms of this number, you write it as some other small number called moles times the number in a mole, and you are free to write it this way. If you write it this way, then you write it as nRT. R is the universal gas constant. It's n times the Boltzmann constant, n0 times the Boltzmann constant. That happens to be 8.3 joules per degree centigrade or per Kelvin. Right? The units for R will be PV, which is units of energy divided by T. So this is what they found out first, because they didn't know anything about atoms and so on. But later on, when you go look under the hood of what the gas is made of, if you write it in terms of the number of, if you write it in terms of the number of actual atoms, you should use a little k, or you can write it in terms of number of moles, in which case you use big R. And the relation between the two is simply this.